So yesterday we looked at washers and just discs in general. And as I said yesterday, that's pretty much the 2-unit method of doing it, other than we're actually setting it up. There is another way of approaching volumes, which of course 2-unit wouldn't look at, and that's this method of cylindrical shells. So instead of taking the slice perpendicular to the axis of the rotation, we take the slice parallel to the axis of rotation. And so here's our random curve again. And so same situation, we want to go from A to B. But now I'm going to rotate, although for the sake of this it's going to be easy to go, let's say I'm going around the y-axis. Okay? So I would take my slice parallel, and if I was to rotate that slice around, I would end up with a hollow cylinder. Okay? Well, if I was to do all of those strips, I'd end up with a solid, bit like, those, what do they call them, babushka dolls? The Russian dolls, where there's one inside another, inside another. And so we would actually build the volume that way. All these cylinders added together would give us the total volume. Well, rather than looking at it as a cylinder, what I like to do, and it's a reasonably common idea, is to unwrap it or unravel it. And if you unravel it, you'll end up with a rectangular prism. Now, the thickness is delta x, because we're going along the x-axis there with our slices. The height of the cylinder would be the y value, but we want it in terms of x, because that's where our thickness is. It's delta x. But that's all right. We know y is equal to some function of x. Now, the base would end up being the circumference of the circle. So 2 pi times the radius, well, in this case, the radius would just be the x value. And so the area face, that cross-sectional area, becomes a rectangle instead of a circle like we saw yesterday. And it'll be base times height, so 2 pi x times whatever the function is. And so the element of my volume, element of the volume is 2 pi x, function x, delta x. And it's the same idea then. So we're saying, okay, well, I want to sum up all of these cylinders, and we're going from A all the way to B, and that becomes an integral. Well, 2 pi can come out the front because they're constants, and it'll be x times function x. Don't make the mistake of just quoting that formula, x times function x, which I have seen people do in the past. Again, the work is in the building of the shape. So, all right, let's have a look. Same question as yesterday. We've got 4 minus x squared, and we're going to rotate it about the x-axis. So it was our upside-down parabola. But this time, instead of taking slices perpendicular to the x-axis, I'm going to take it parallel. So we get a horizontal slice. And if I was to rotate that, there's my cylinder I would get. Well, if I unwrap my cylinder, I get there's my rectangular prism. The thickness, we want it all in terms of y, our sides. So the height will be, in this case, it's going to be twice the x value. So it's a symmetric shape. There's x on either side of the axis there. So that's 2x, but I want it in terms of y. So when I rewrite this, I get x is 4 minus y to the power of a half. So we end up with a width of our rectangle here of 2 times 4 minus y to the power of a half. The height of this one would be the circumference of the circle. So 2 pi times the radius. The radius in this case is the y value, so 2 pi y. So the area of that cross-sectional face will be 2 pi y times 4 minus y to the power of a half. Putting that all together, there's my volume element. So 4 pi y, 4 minus y to the power of a half, delta y. We're summing from, this is where you've got to be careful because we're so used to just going around the x-axis and using the x values. It's all in terms of y. So we're going from 0 to 4. 0 to 4. That becomes our integral. So the integral is y, 4 minus y to the power of a half. Looks like a horrible one to do, but one of our techniques we saw in 4-unit integration. I notice I'm going from 0 to 4. Remember, we can always replace x, or in this case y, with 4 minus y in this case, so whatever we're going up to. And so if I swap those, everywhere I see a y, I'm going to substitute in a 4 minus y, that becomes a lot easier to integrate because I can actually expand that out now. I couldn't expand out the 4 minus y to the power of a half. So expanding that out, it then becomes a simple, well, it's not a polynomial, but add 1 to the power over the power, substitute in, and we'll see we get the same answer as we saw yesterday, 512 pi on 15. That may not be the best method to do that particular problem, but that's just to show you that, hey, it works. I mean, it doesn't matter which method we use, we're still going to come up with the same sort of answer. Let's have a look at this one. We're going to get a circle and rotate it around the line x equals 4. So there's our circle. Going to rotate it around x equals 4. We end up with a donut. If you think about rotating a circle around a line. So we're going to end up with a donut. So my slice, in this case, is parallel to the axis of the rotation. So it's a vertical slice. Rotate it round, there's my cylinder. And just to sort of get a feel for the donut, I don't know if that helps there, but imagine rotating all the circle round and you get a donut. Of course, the technical name is not donut. The mathematical name is, of course, torus. So let's get back to our problem. Unwrap our cylinder. The height of our cylinder in this case will be twice whatever the y value is. Because again, we've got that symmetry above and symmetry below. But the thickness is in terms of x, so I want that 2y in terms of x. Well, we know x squared plus y squared is 4, so I can rewrite that one, and I get y as the square root of 4 minus x squared. And so we've got 2 lots of that. Now, this is where we've got to be careful. The circumference is 2 pi the radius. The radius in this case is not just the x value, because we're going around 4. So it'll be 4 minus whatever the x value is, will be the radius. So we'll have 2 pi 4 minus the x value. Well, let's put that all together. Okay, so the area of that cross-sectional face, 2 root 4 minus x squared, times that by 2 pi 4 minus x, we get our volume element. Oh, actually, I've tidied it up first. There's my volume element, so 4 pi 4 minus x, square root of 4 minus x squared. That's what we have to integrate. Looks horrible, but we can actually do it without doing any integration whatsoever. Watch this is amazing. So let's set up our sum. We're going from, in this case, it's the x values. And don't think of the whole rotation, just the original shape. The original shape, the x values, is going from minus 2 to 2. All right, so this is what we have to integrate. 4 pi I can factorise out. Going to split this up into 2 integrals. I'm going to say 4 times the square root of 4 minus x squared, and then x times the square root of 4 minus x squared. Okay. Now, the very first one, 4 times the square root of 4 minus x squared. Oh, that's tight. Yeah, okay, I'll take the 4 out. Square root of 4 minus x squared. What am I looking at? It's a semicircle. So I don't need integration. I can use my formula for the area of a circle. Okay, so there's my semicircle. Now, so 16 pi, half of pi r squared. Now have a look at the other one. In this nice question, we're going symmetry from minus 2 to 2. X is an odd function. The square root of 4 minus x squared is an even function. Odd times even is odd. Integrate an odd function around symmetry, that's just equal to 0. So if you notice that, you can save yourself a lot of time. So that'll just be minus 0. So all right, tidying that up, there's our answer, 32 pi squared. So how to integrate without actually doing any integration there. Okay, so same sorts of questions, just a different technique. As I said yesterday, I've picked questions out. I may have picked, in the Patel ones, I've given you the problem to do by cylindrical shells, whereas it might have been more efficient to do it the other way and so on. But that's just for the fun of it. The Cambridge exercises are set up in 6A is discs and washers, 6B is cylindrical shells, so those ones should be okay.